In this video, we introduce the linear unobserved effects model for panel data, as well as the fixed effects estimator. This lecture continues our sequence of lectures on the linear panel data model. Last time we talked about the linear model in the cross-section. This time around, we'll actually talk about panel data explicitly and introduce a method for estimation thereof, or actually two, known as the fixed effect estimator and first differences. First differences will be in the following video. Just as a reminder, when we talk about cross-sectional data, our structure looks something like this. Each row represents a different individual, and we have data both on the outcome variable as well as a collection of regressors x1 through xk. When we talk about panel data, we have an additional dimension to work off. Namely, when we talk about panel data, for each individual, say individual I or 1 in this case, we have repeated observations across different periods in time, subscripted here by this lowercase t, and here for 3 periods of time. That is, we observed both the outcome variable across all these periods of time for the same individual, as well as all of these regressors. Now, having introduced this additional dimension of our data, let me just rehash some of our standing assumptions and try to clear up some possible confusions. Now, in this course, we still assume that observations are independent and identically distributed across individuals. The only addition here is that when we talk about an individual, we are talking about a cross-sectional unit which is observed for t time periods. So the data for an individual here, when we talk about the data for an individual, we mean yit and xit for t running for t capital T periods of time. Note here that when we say that observations are IID, or independent and identically distributed across i's, we may still, and may have indeed, dependence across time within a given individual. In fact, that is to be expected. Now, we will still focus on asymptotics, and we'll still focus on asymptotics as the number of individuals, the number of i's, capital N, grows without bound. Hence, when we talk about limits of various objects, or whenever you see an arrow, you should understand this arrow as n going to infinity, holding the panel dimension, or the number of time periods, capital T, fixed. An implicit assumption for this type of asymptotics to be relevant is that the cross-sectional dimension n is much larger than the panel dimension t. A good example of a data set which is suitable for, or which satisfies this type of assumption, are the various Danish registers, where we see millions of peoples, millions of Danes, across maybe a time span of 10 to 25 years, something like that. Now, the outline for the rest of this video goes as follows. We'll introduce the linear unobserved effects panel data model, and then we'll move on to talking about the fixed effect method of estimation for this model. That involves a discussion of the within transformation leading to the fixed effect estimator, and then we'll talk about various conditions leading to both identification and consistency, as well as a discussion of efficiency and methods for estimating the relevant variance matrix, thus allowing us to do some sort of inference. First on the platter is the linear unobserved effects panel data model. Let me just pause for a second here before I throw the model on a slide and ask, why should we care about using panel data? That is, what is the motivation? Now, typically in econometrics, our object of interest here is to estimate some sort of partial effect from a population regression function. Now, when we're talking about when we specified a linear population regression function, as we've done here, partial effects are directly translated into the coefficient, or they're directly related to the coefficients, here denoted by beta. Now suppose that we want to estimate these partial effects of a population regression function while controlling for some additional variable c. So here c connotes controlling or control variable. But suppose now that this variable c is in fact unobserved. This may or may not be a problem depending on what we're willing to assume, but usually we should, if we're interested in controlling for c, it's probably for a good reason, and we should worry about omitted variable bias. Now, for the purposes of this course, this constitutes a major motivation for using panels. Namely, we want to account for unobserved individual heterogeneity as represented by C. Alright, so the linear unobserved effects panel data model goes as follows. Our equation of interest is still a linear one, but here I'm writing out that the outcome y for some arbitrary cross-sectional unit or individual I is linear in regressors xit up to unobservables, where now we have two of them, one being what we'll call ci, or the individual effect, plus uit, which you could think of as exactly like ui for the cross-sectional model. Now here I'm explicitly writing from t running through 1, 2, all the way up to capital T, so to denote, to highlight that we have repeated observations for the same individual. Now, if we were to add the assumption that this one unobservable term, uit, has conditional mean 0 when conditioning on the regressors from the same time period on top of this individual effect or individual unobservable, ci, then we'd get an expression for the conditional mean of y, namely that it is conditioning on xi's from the same period, it is linear in those xits, and it is also linear in the unobserved effect ci, which brings us back to our previous slide when we motivated the panel data model. Now note here that this additional unobservable ci is implicitly assumed to be fixed over time. That is, it doesn't even carry a time subscript. That is a restriction that may or may not be restrictive, or may not be strong. Now for the purposes of the discussion that follows, let's denote the type of exogeneity as imposed in this equation 1 as contemporaneous exogeneity, or if you want to be specific, contemporaneous exogeneity of the xits, conditional on the unobserved effect ci. Now a natural question to ask is that, given our linear model, and given this working assumption of contemporaneous exogeneity, can we just ignore the presence of the unobserved effect, that is the ci, and just use OLS, our good old friend ordinary least squares? To be specific here, by using OLS I mean that we use pooled OLS, where we completely ignore the time aspect of the data and just treat each IT pair as a separate observation. Now for answering this question, it may be convenient here to just collapse the error term of the model and introduce this composite error, VIT, as the sum of CI and UIT. That allows us to write our previous linear linear unobserved effects model for panel data in this manner. Now, if we're ignoring that different observations can arise from the same individual, and we proceed using pooled OLS, then we know that pooled OLS is consistent provided that the regressors, in our case the XITs, are uncorrelated with the error term, which in this case is this composite error term. Well, expanding on the composite error term, we see that this expectation is the sum of two components. One is the expectation of the product of the regressors and the individual effect, CI, and the other is the expectation of the regressors and the additional unobservable, the UITs. And iterating the latter expectation, we see that this is 0 under our working hypothesis, working assumption of contemporaneous exogeneity. Hence, in order for pooled OLS to be consistent, we require at least that the individual effect is also uncorrelated with the regressors in time period t for all time periods. Whether or not we're willing to make this assumption depends on the case, but usually we would be worried here about the omitted variable problem, and we would have to do something else. That is, pooled OLS is not necessarily a good idea. Since pooled OLS is not necessarily the best idea, we'll discuss various panel data estimators which rely on various empirical strategies. These estimators can roughly be divided into whether or not they believe in the previous assumption. Now, if we don't believe in it, which is to say that we don't believe the regressors are uncorrelated with the individual effect, then we arrive at estimators called the fixed effect estimators and the first difference estimators. Now, these estimators, which we'll discuss in detail in the slides to follow, as well as the next video, they have a common feature in that they both seek to transform the data in such a manner that the individual effect is effectively eliminated from consideration. Now, if we are to believe that this uncorrelatedness assumption holds, then, as already discussed, we could use pooled OLS, or instead of ignoring the time dimension completely, we might take it into account in some sort of generalized least squares procedure. Now, a particular implementation of generalized least squares for the linear unobserved effects model for panel data leads to what's known as the random effects estimator. Again, generalized least squares doesn't necessarily affect consistency, but it may help us achieve a more efficient estimator under additional assumptions. All right, so let's discuss the fixed effect method of estimation, starting with the within transformation, thus leading to the fixed effect estimator. All right, so going back to our linear unobserved effects model for panel data, let's introduce a piece of notation here. Namely, let bars, whenever you see a bar on a variable, let the bar on that variable denote the time average of that variable for a given individual. For example, when we're talking about the outcome variable here, yi bar denotes the average of all the YITs over time. Now, since we've fixed the individual, these variables, these barred variables, will still depend on the particular individual that we look at, hence they should carry the subscript I. Now note that if we were to think of the individual effect Ci as being time varying, we could also construct the time average but it would be simply the variable itself, namely CI. In fact, it doesn't make much sense to talk about its time average, since we haven't even endowed it with a subscript t. Now, if we take our linear expression up here, and we average both the left and right hand sides, then given the linearity, we can collapse these capital T equations into a single equation, stating that the time average outcome, y, is linear in the time average regressors up to the unobservable CI, the individual effect, and the average of the UITs. Hence, if we take our original equation and subtract this time averaged equation in any period, say 1, 2, all the way to capital T, we arrive at a time averaged equation. And we see that, so now on the left hand side, we have the time averaged outcomes as a function of the time averaged regressors up to the time averaged unobservables. Now, since the CIs are time invariant, that is, they don't vary over time, this subtraction leads us to cancel out CI. But that's fantastic news if the CIs were a big worry to begin with. Now, let us introduce an additional piece of notation in order to write this expression in a more convenient form. That is, let dots or double dots denote a time demeaned variable. That is, a variable where we've subtracted the time average. Again, for the outcome variable. Let's talk about the outcome variable in detail here. So here, YIT with double dots over just denotes the original YIT, the outcome for individual I in period t, upon subtracting the time average for the same individual. Then we may express the previous equation as a linear equation relating the time demeaned outcomes to the time demeaned regressors up to the time demeaned unobservables, the time demeaned UITs. So I should probably pause and say, this idea of time demeaning is often referred to as within transforming the variables, or sometimes loosely speaking, within transforming the data. And as we see, by our assumption that the individual effect is time invariant, it allows us to cancel out the individual effect. Hence, we arrive at this estimating equation relating time demeaned variables to each other. Note here that except for the time invariance, we have imposed no assumptions on the individual effect. In particular, so far, we could still allow for arbitrary correlation between the regressors in any time period, as well as when compared to the individual effect. However, you should remember that if we were to take this equation to the data, or if we were to try to estimate this equation, we would still interpret the coefficients appearing in this equation from the original, or what we may think of as the structural equation. This is only an estimating equation, which we've arrived at through manipulation. At this point, it may be helpful to visualize what the within transformation actually does. So here I've scatter plotted, simulated some data on X and Y, and scatter plotted the resulting observations. Here I've simulated data for a handful of individuals and for 10 time periods. And additionally, I've colored the observations according to which individual they belong to. For example, this cluster of red diamonds belong to the same individual. Now, if we were to use pooled OLS, it would lead to the fitted line or regression line given here by the given here in blue. And we see that pooled OLS, or if we were to take the pooled OLS regression line seriously, it would lead us to conclude that y and x are positively related. However, if we demean the data, that is, we subtract the time averages for each individual and plot the resulting within transformed observations, it would lead us to a completely different conclusion, as depicted in the bottom picture here. In fact, upon demeaning the data, we are led to believe that the relationship between x and y is in fact negative. So the within transformation may matter a great deal for the conclusions that we reach, and again, this highlights that pooled OLS need not be what you want to do. Alright, so what is the fixed effect estimator? Well, the fixed effect estimator, in essence, it is just pooled OLS having within transformed the regressors as well as the outcome. So here I'm writing out the pooled OLS estimator explicitly using the within transformed regressors, the XITs with double dots, and the outcomes with double dots. Now this expression illustrates that we're pooling, but for computational purposes, it might be fruitful to write this in a more compact format. So let's stack the within transformed regressors and within transformed outcomes over first time and then individuals in order to obtain an n by t, nt by k, regressor matrix, and an n by t, nt by 1 outcome vector. Then we may write the fixed effect estimator in this more compact format, which runs completely analogous to OLS, the OLS estimator for cross-section data. Oops. Now, you may ask, how would you conduct the within transformation in practice? Well, suppose that we've gathered the regressors here, the XITs, we've stacked them over time for a given individual to get a T by K matrix. Let's call it boldface XI. And similarly, stack the YITs for a given individual to get a T by 1 vector of outcomes for a given individual. Then we may simply multiply this matrix or vector respectively with what we could think of as a time demeaning matrix, in Wooldridge notation denoted QT. This time demeanor is just the T by T identity matrix upon subtracting 1 over T times the outer product of these JT vectors, where the JT vectors are just a T by 1 vector of 1s. Hence their outer product results in a T by T matrix consisting solely of 1s. Now you get experience with this sort of transformation and other transformations in the exercises. Now the sharp student may at this point have scratched their head multiple times upon realizing that when we introduce CI, we could also just think of this unobserved effect as corresponding to an individual-specific intercept, right? So you may ask, why don't we just proceed with estimating these additional n intercepts, or all of these individual-specific intercepts? That is, we treat the CIs as constants or parameters to be estimated. Now one may show that, well, this procedure already exists, and it's known as the least squares dummy variable estimator. Least squares because we use a least squares procedure, dummy variable because it amounts to just adding a dummy variable for each individual, all n of them, to our existing list of regressors. Now, one may show that time demeaning, or the within transformation, sometimes just known as going within, time demeaning yields an algebraically identical estimate of the beta coefficients. So from that point of view, we might as well do least squares dummy variables because it leads to the same beta estimates. However, from a computational point of view, the least squares dummy variable estimator is quite burdensome. In adding all of these additional regressors, we'll be carrying around very large matrices. Also, the resulting estimates for the CIs, when thought of as parameters, will not be consistent, at least not in the usual case where we send n to infinity. The reason here is that the number of parameters, that is all of these individual specific intercepts, increases directly with n, the thing that we're sending to infinity. Hence, for each new observation that we encounter, we introduce an additional variable. Having introduced the fixed effect estimator, we can move on to thinking about various properties of this estimator, such as consistency. This will also yield assumptions under which the model is identified. Now, one way to thinking about identification is that we need suitable analogs of assumptions OLS 1 and 2 for the transformed data, or within transformed data. Now, note here that the orthogonality condition, which resembles or which amounts to OLS 1 for the transformed data, does not follow from our previous assumption of contemporaneous exogeneity, which is what I've repeated here in the displayed equation. The reason here is that contemporaneous exogeneity, where the same t appears in the variable that we are conditioning on and the variable that we are computing the expectation of, does not restrict in any shape or form the relationship between the regressors in other periods and this outcome in period t. Unobservable in period t. However, when we look at these within transformed variables, both of these include time demeaning and are therefore based on the xits and uits in all time periods. Hence, in this product, again, this product, when we expand on this product, we must necessarily encounter products of xit and uis for different time periods, that is, t different than s. So we need a stronger assumption. That assumption, the assumption that we will work with thus far, is called strict exogeneity, and we will label it FE1 for fixed effects 1. The assumption states that the conditional mean of the unobservable UIT, upon conditioning on both the individual effect and the regressors in all time periods t through capital T equals 1 through capital T, is equal to 0. Now this conditional mean 0 assumption, or FE1, in words, will say that the regressors xit collected over all time periods is strictly exogenous, conditional on the individual effect, or simply, for short, and when the context is clear, that the regressors are strictly exogenous. Now, this assumption of strict exogeneity implies that the conditional mean of the within transformed UIT conditioning on the within transformed XIT is equal to 0. Now this result, or this implication, follows from the within transformed XIT being a function of the XIS's gathered across all time periods, and a simple application of the law of iterated expectations, which I encourage you to do. Check. Hence, under the assumption of strict exogeneity, assumption FE1 or fixed effects 1, the analog of OLS1 is satisfied on the transformed data. Having our orthogonality condition satisfied, we also need to discuss a suitable rank condition. So let's stack the within transformed regressors and outcomes into individual specific matrices and vectors. So here this boldface xi with double dots arises from stacking the xits over t to get a t by k matrix. And this boldface yi with double dots arises from stacking the within transformed yits over t for a given individual, thus yielding a t by 1 vector. With this notation, we may write the fixed effect estimator in a format which looks more like the cross-sectional version of the OLS estimator. That is, we've written it as the inverse of the average of the within transformed regressor product and the average of the within transformed regressors and within transformed outcomes. Now having multiple outcomes since we've stacked the outcomes over time. Now an analysis running parallel to the cross-sectional case, the linear model for cross-sectional data, reveals that the relevant rank condition is that the expected product of the within transformed regressors should have full rank. Now this here is a k by k matrix, so full rank means that it has rank k. You may also expand on the product of the within transformed regressor matrices and then pull the expectation inside each part of the sum to show that this amounts to assuming that the sum of the time-specific expected products of within transformed regressors should have full rank. With these two assumptions, strict exogeneity as well as a rank condition, we can establish consistency of the fixed effect estimator. The argument runs parallel to the cross-sectional case, but let's just go through the basic building blocks. So let boldface UI with double dots collect the t by 1, the t within transformed UITs for a given individual. Then we may substitute in the model to express the fixed effect estimator as the parameters that we're trying to estimate, plus the product of two terms. Again, this product takes an average, takes the form of the inverse of an average of regressors, here being within transformed regressors. The second product, the second part of the product, also takes the form of an average, where we're averaging over the product of the within transformed regressors and within transformed unobservables, the UITs. By our assumption of IID data being independent and identically distributed across I's, and having organized our estimator in this way, where we're looking at averages of I's, we can invoke the law of large numbers, and also using the fixed effect assumption 2, which was our rank condition, and Slutsky's theorem, in an argument that runs parallel to the cross-sectional case, we can show that the inverse average product of the within transformed regressors converges in probability to the corresponding inverse, or the inverse of the corresponding expected value. Also, invoking the law of large numbers, we can show that the second part here, the second average, converges to its expectation, which in this case is the expectation of the within transformed regressors times the within transformed unobservables. Now, if we flesh out the components inside this expectation, we can write it as the sum of the product of the time-specific within transformed regressors and time-specific within transformed unobservable. So that we can pull the expectation inside each part of the sum here. And now we see that by our assumption of strict exogeneity and using the law of iterative expectations, we can show that the whole thing is in fact 0. From this, we can conclude that under our strict exogeneity assumption and our rank condition on the within transformed regressors, the fixed effect estimator is in fact consistent. At this point, I would like to bring a caution to mind, which concerns time constant variables. Namely, if there are any time constant variables in XIT, that is, variables which do not vary across time, then they'll net out in the time demeaned XIT. That is, if we subtract their time average, and they don't depend on time, then that time average must be the variables themselves, so their difference must be 0. As a result, when we look at this T by K regressor matrix of within transformed regressors, this matrix will have a 0 column. And for the same reason, when we take its product, the product with itself, it must result in a matrix which has less than full rank, and therefore has less than full rank when we compute the expectation as well. As a result, when we're talking about fixed effects methods, we cannot include variables which are time constant, since the rank condition fails. For example, we cannot involve or include variables such as gender or ethnic origin, or even an intercept. This is somewhat disappointing this would be somewhat disappointing if those are the variables that we actually care about. In that case, we should use a different method, and we should try to work out other assumptions which would lead us to estimate the coefficients of such variables in a consistent manner. Now, the intuition for why we cannot include these types of variables is that we simply cannot separate the effects of time constant variables from the individual specific effect, the CI, which is also constant over time. Since we cannot separate these effects from each other, there's no hope of estimating them consistently. So let's spend a moment thinking about the interpretation of strict exogeneity. Going from our original linear expression and invoking our strict exogeneity assumption on the unobservables, that is the UITs, we can write the conditional mean of y in period t, conditioning on not only the individual effect, but also the regressors in all time periods. We can show that this reduces to the conditional expectation conditioning only on the individual effect and the xi in the same time period, which we assume to be linear in both variables. In words, this means that upon controlling for ci and xit, regressors in other periods have no partial effect on the outcome. So that's the interpretation. Is it restrictive, you may ask? Well, as we'll show later on, this assumption, that is, the assumption of strict exogeneity, cannot hold if the regressors contained lag-dependent variables. For example, if xi contains the outcome from a previous period, such as the one right before. In fact, the assumption of strict exogeneity, or FE1, is violated for these types of dynamic panel data models, and also rules out other forms of dynamics, such as feedback. This is particularly important when we model, or when we intend to model intertemporal decisions. At this point, it may be fruitful to go through an example. So let's talk our way through an example concerning fertility and female labor supply. For this example, let y be an indicator, that is a 0-1 variable, for whether a woman works or not. And let x be the children of the household of age at most 2. I think it's fair to say that women and families altogether plan when to have children in an intertemporal manner. Children don't just show up at the doorstep one day. So we're talking about a model involving intertemporal decisions. Now let I denote a woman which in some period t receives an employment shock, as captured by this unobservable UIT being negative. Think strongly negative. This may be the case if the firm in which the woman works at suddenly closes. Now, in the case of a firm closure, woman I in period t loses her job, which we may write as YIT being 0. As the woman goes from working to not working. Now, having all this time on your hands, the woman or the household altogether might decide that this may be a good time to try to have a child, such that it may increase the probability of having a child in the following year. In our notation, xi in t plus 1 is 1. Now note here that from this story that I just told you, we've created a relationship between the unobservable in period t and the regressor in the following period. Hence, our conditional mean 0 assumption is violated. Now, this type of feedback is not too far-fetched, and it in general violates strict exogeneity. Moving on to talking about efficiency. Well, having established consistent estimation, we may think about whether we can also obtain efficiency under some assumptions. So, for the purpose of stating the following assumption, let's gather the regressors in all time periods into one long vector xi, which is of length k by t, or kt. Let the third fixed effect assumption, fe3, be the assumption that the expectation of this matrix, t by t matrix of the UIT unobservables when stacked in vectors, given regressors in all time periods, as well as the individual effect, is in fact a scalar matrix, by which I mean it reduces to the identity matrix, the t by t identity matrix, up to a proportionality factor, say sigma square u. This type of assumption is a homoscedasticity type of assumption, but it also captures much more. Well, it captures certainly homoscedasticity in the sense that the UITs across time have the same variance as represented by the diagonal of the above matrix. It also means that they are serially uncorrelated, that is, that there's no serial correlation, in that the off-diagonal terms of this matrix are all 0. But it in fact also it is in fact a much more loaded assumption, in that we are assuming that conditioning on xi as well as the unobservable ci has no impact on the shape or form of this matrix. That is, that all of the conditional variances of the UITs are 0, and their conditional variances of the UITs are constant, and their conditional covariances are all 0. Now, even without FE3, we can show that under assumptions FE1 and 2, the strict exogeneity assumption and the rank condition that we introduced, that the difference between the fixed effect estimator and the coefficients that we're trying to estimate, when scaled by square root n, converges in distribution to a normal distribution with a variance of the sandwich formula and 0 mean. Now, the argument here runs completely in parallel to the cross-sectional case, which we covered in the previous video. In this case, the asymptotic variance, what we may think of as V, has a bread matrix, the A matrix, or rather its inverse, but the A matrix is the expected regressor product, where the regressors are now the time averaged, the time demeaned, or within transformed regressors. The breadth of this matrix is slightly more complicated in that it involves both the within transformed regressors as well as the vectors of unobservables, the UITs. However, it may be fruitful to think of the cross-sectional case here, in which case the version of B would be UI xi prime, UI xi prime primed. I'm running out of space here. Let me scroll this a bit back. Which, since UI is scalar, just reduces to UI squared, or the expectation of UI squared, the outer product multiplied by the outer product of the regressors. In this case here, we're dealing with a UI, which is a vector, so we can't just place it wherever. We have to take into account that the different dimensions must match. That is, that these vectors or matrices must be conformable. But I think it's from the cross-sectional case, we recognize the same structure. Now, under our assumption, this homoscedasticity and no serial correlation type of assumption, the B matrix, which is written in this manner, can be calculated in 2 steps using iterated expectations. Now, since the within transformed regressors are just functions of xi, upon controlling for xi, they can be thought of as fixed. So we can pull the expectation, the inner expectation, inside until we hit the UIs, or the product of the UIs. And under FE3, this matrix, or the inner expectation, just reduces to a scalar matrix, that is, the identity up to a proportionality factor, sigma square u. Now this calculation here shows that our B matrix under FE3 is just proportional to the A matrix, the inverse of the bread. So as a result, the asymptotic variance, RV from upstairs over n, is just sigma square u A inverse divided by n. And in the displayed equation, I just substituted for A. Now, since we have this structure of the asymptotic variance, it now following the argument for the cross-sectional model, one may show that the fixed effect estimator is asymptotically efficient under these 3 assumptions. Lastly, we'll think about how one may estimate the variance matrix under various assumptions, which would allow us to do inference, say, using the WALT test procedure as discussed in the previous video. Now under our 3 fixed effects assumptions, FE1 through 3, a consistent estimator arises from replacing any unknowns in the asymptotic variance. That is this matrix with an inverse, replacing unknowns with consistent estimators. We already know how to estimate the A matrix, so we plug in, well, we know that estimating the A matrix can be done by appealing to the law of large numbers, or the analogy principle. So we let our A hat be simply the average of the product of time d-meaned regressors. What's left to do is to estimate sigma square u, and here we're going to use the sum of squared residuals. This is the sum of squared residuals from our fixed effects regression, suitably averaged. Now one may recognize that this is almost the standard OLS variance estimator using the transformed data. However, there is a potential pitfall here. Namely, as you may see from the highlighting done here, we are subtracting more inside the denominator here than our usual k degrees of freedom correction. In fact, we're subtracting n as well. So there are fewer degrees of freedom. The reason for subtracting these additional n is our implicit estimation of individual intercepts. Think back to the algebraic equivalence between the within transformation or fixed effects estimator and least squares dummy variables, where we explicitly estimated n individual specific intercepts. Now here, without the minus n, or without the subtraction with n, the resulting estimator can be shown to be inconsistent. So the subtraction of n is not just a fluffy degrees of freedom correction like the subtraction of k. It doesn't vanish asymptotically. It matters because the n is exactly what we send to infinity. Now in practice, what does this mean? It means that if you've manually conducted the within transformation and you are applying, say, standard regression tools using your within transformed data, then you cannot rely on the standard OLS form or the standard variance estimator as automatically spit out by this least squares routine or regression routine. In fact, one may show that the resulting standard errors are too small, since they neglect to subtract the minus n resulting from the individual specific intercepts. However, if you use a canned estimation routine, such as the one that's built into, say, Stata, then you can recover the asymptotically valid standard errors by simply subtracting the results by the following factor, which is the square root of the degrees of freedom that would prevail if we did not subtract or did not adjust for the estimation of individual specific intercepts relative to the degrees of freedom that take these intercepts into account. Lastly, this whole discussion on the previous page, or the previous slide, is only relevant if we actually believe in the assumption FE3, that this type of assumption of homoscedasticity and serial uncorrelation. Or I should say that fixed effects 3 rules out heteroscedasticity and serial correlation. Of course, this assumption may or may not be violated in an empirical setting. So it would be nice to have an estimator which is robust to FE3. And the following estimator does exactly that. And it's given here in displayed equation, where we are using a formula that is very similar to the one for the cross-sectional case. In fact, one may see that this estimator is really just A hat inverse, B hat inverse, or B hat, A hat inverse over N, where we're using A hat as before, but now B is slightly more complicated, since we cannot algebraically eliminate B from the asymptotic variance. Now note here again that in the cross-section, the corresponding B, or B hat, in the robust variance covariance estimator would be the average of the squared residuals multiplied by the outer product of the regressors. Again, this runs completely in parallel, or our robust variance covariance estimator here is completely analogous to the robust variance covariance estimator, or the heteroscedasticity robust variance covariance estimator in the cross-section case, except that we have to take into account that our residuals here are vectors of dimension t by 1.